So this is the last sprint, sprint 9, final sprint. So to start, I'm going to go over the collision stuff that we have added. So here's the collision map. So we've got our collidable. Collidable has a collision volume, which can be a ABB, OBB, or bounding sphere. You can register and deregister from being collidable. You can do test self or test pair. The collision manager keeps track of all of the commands for test self and test pair, as well as group delete commands, which are for the collidable groups, so that they are removed at the end of the game closing. Since they are singletons, all of the test pairs are part of the command test base, and the groups are part of the group delete base, so that I cannot accidentally register these things to the wrong group and call them at the wrong time. Other than that, we also have the collidable volumes, so just the collision volume, which can be a bounding box base, which is set up so that ABB and OB collision mix together well, and then there's also the bounding sphere. So a bounding box base just has a world matrix, half diagonal scalar, and world center, because those are the things that are required for an ABB to do OBB collision. Otherwise, they just have centers, maxes, and mins for themselves, and a center and a radius on the bounding sphere. So to go over collision, first I will look at the user code. I'm looking at a demo right now that I created, so it's a little simpler to go through. Let's look at the ship. So you just got your virtual void collision, and then you call collision for whatever object you registered to collide with. And in here, you got to set your collider model with what the model is, and then what type you want it to be, which is rather OBB, AABB, or bounding sphere. You then register for collision and deregister in the deregister object. In the update, you update your collision data. And then down here, you got your callback for when you have collided. So, for example, this one's just going to change colors. So, pretty self-explanatory there. Pretty simple, pretty simply much the same as what we did before. I'll walk through the registration, or if I can, yes I can. So, just goes to this collidable. Collidable calls the scene to be registered, then creates a collision registration command for that collision, or that collidable, which just has the pointer, the collidable, and then calls the specific group that it wants to be registered into. So that's pretty self-explanatory there. For the scene, then, sorry, up here, the user just calls set collision pair between two things, which is part of the scene, which then creates a command for test pair, which is registered to the collision manager to be called every frame to test against collisions. I'll go over this in a bit, but moving on to the next thing. So there are no graphics objects tied to my specific volumes that are selectable by the users. So now we'll just go over those different collidable volumes. So our meshes here. Start off with the collision volume, which is the virtuals for the enters, which is just the double dispatch things. So we have the first one that is always called, and then the other three are what is called after, one for each collidable volume. And then there's also the terrain collision for terrains, which we'll talk about later. There's also an initialize, which is set up for the ABBB and the OBB, the compute data for all of them, so that every frame the collision is updated correctly if the object moves, and then a render, which is for the visualizer. If the user wants to call just render the collision volume for whatever game object I'm in, they can do that. So to start off, there's the bounding box base, which is for the ABB and the OBB. They just have accessors for all of their set things that are in them, which are needed for OBB collision. So an ABB then has its setup, which is mostly for this one is for terrain cells, so that there's an easy way to create a terrain cell with a max and a min only. Otherwise, they use the initialize, which gets a model, sets up all its data. Compute data is called every frame to recompute the position of the ABB. The compute for group data is for collidable groups, just to fix their ABB data. So this takes a max and a min, and then the radius, which is just how big that how big that collision volume is, or sorry, the radius is how big the bounding sphere's radius of all those objects that are in that group are, so that it encompasses everything no matter what. If you get max and a get min, and the render that I talked about for the visualizer, which just shows the ABB, since this is an ABB, and the inters, which are for the double dispatch. So this is the first one, just calls the collision volume of the other collidable with its inner 2 on this, which then allows one of these to be called, which is the same for all of them. And then just the terrain collision, which just has a different math tool for each type of collidable volume. So bounding sphere, much simpler, just compute data, get center, get radius, render the terrain, and then the double dispatch things. And then OBB is the initialize, like the ABB, compute data, get max, or get min, get max is also set up in here. The get center, and then the render, and all the double dispatch, as well as the terrain. So that's all of those. So moving on. Date intersection visitor pattern. So yeah, they all use visitor pattern, as I've shown. And so next is the OBB intersection. So I went with the projecting onto a vector and calculating if they are colliding that way by using all 15 axes. The way to show that would be in the math tools. So just go here. So it's the same for the ABB and the OBB, since they just take bounding box bases instead of specifically an OBB or an ABB. So test projection just calls the test projection overlap on the 2 bounding boxes, as well as with all 15 of the different vectors that it would be projected onto. And then, oops. This just checks to make sure that the mag squared of the vector is on 0, so that you don't get incorrect data. Sets that vector to a pure vector, and then calculates the projection across D, which is just takes the 2 centers and the vector, calculates the projection from the distance the distance between the 2 centers onto the vector, and gets you that distance. Then have the calculate projection, which takes the vector and a bounding box base, which gets the projection from the center to the edge on that vector, using the half diagonal for that ABB or OBB. And then you simply add those together and check if they are smaller than the distance between the 2 centers. And if the distance between the 2 centers is bigger, then those added together, you return false. Otherwise, it will come out with true, which then they are colliding. So this is an OBB and an ABB. I mean, it works. I've showed in different other videos that it works. It's harder to show now because of the tiered collision. But that's all good and dandy. So then for the collidable groups, which would be next. So a collidable group now has a group ABB, which is used for the test for the tiered collision. So we have the delete, which is to delete the instance when you are done with it, and register and deregister to the group, and then we have the update. So the update updates the ABB for the group, and then I am just visualizing it down here, but this simply calls the compute data with the correct information for the whole group so that it can update the ABB for the group, and then I just have an accessor for that group ABB. As for calling that, the collision manager has a list that it is registered to for the group update command, which just executes the update on all of its managers that it's keeping track of, all of its collidable groups that's keeping track of before executing all the tests, so that you have the newest frame data for that group ABB. As for commands, I'll go over the commands that we're working with now to show the tiered collision better. So let's go down here to collision. So the deregister and register are the same as before, as well as the group delete command. Those are just the same as they were back in the last class. So this is the update command, which just calls the update for the group. And then we have the test pair command, which when executed, it gets the group ABB and tests them against each other. And then it gets the collection 1 and tests the collection 1 against the group ABB of the second group, and if one of those is true, then it will check with against collection 2's group against the ABB of the first group. So if the bounding sphere is colliding with other ABB, then it checks if an object in that one is colliding with the other ABB. If those are both true, then it checks the bounding spheres of those two objects against each other, and then in the end, it will then check the user's selected bounding volume against each other, and then it will call if those are correct. So to show here is just two objects. They both have collision volumes. So the groups are the yellow boxes. So when the group starts colliding with the other group, the second group's bounding sphere is being checked against this one, and when those start colliding, then this bounding sphere starts checking against this ABB, and when those are both true, then these turn blue because they're then checking against each other, and when that's true, then it will start checking the user defined against each other. So as you can see right now, they're all colliding, but if I were to go like this, sideways where the bounding spheres are not colliding, those are obviously colliding, but it is not registering as collision since the bounding spheres are not colliding. So that's just me showing off the tiered collision. That's between an OBB and an AABB. With a bounding sphere, I mean, it'd be the same thing, but obviously it would be going off whenever it hits that bounding sphere. As for self, it just checks the bounding spheres first against each other and then does the user selected volume. So that's my two tiered collisions. Then we have the terrain test collision, which I'll go into more detail again when I get into terrain, but it just gets the group ABB max and min. Then I get the cell block in for the iterator for all those cells that are within that max and min, and then I test those cells against the ABB of that group. If that's true, I then check individually the objects in that group against the bounding sphere of that object against the terrain cell. If that's true, then you do the user selected against the terrain cell, and then I'll get my callback if that's true. This is just the group delete base, test base, and update base, all the same. Like I said, just so I don't accidentally register them to the wrong things. Let's see here. New. As for the destructor, so we've got our collision manager, which just when it goes away, it calls the group delete commands on all of the collidable groups, and then it deletes, clears all of its commands. So as you can see here, we've got our collidable collision group managers deleted, and the 2 groups that it had on it are also deleted. So for collision, everything's being deleted correctly. All of my math tools are using const references, so all of that is going through as const. Yeah, and then the terrain collision I will talk about when I talk about terrains more. But other than that, that I believe is everything for new collision stuff. So yeah, next I will talk about the visualizer and the math tools.